Hi everyone. Today we're going to discuss partial derivatives. Now that might sound a little bit scary. They're a part of multivariable calculus, which I'm sure sounds even scarier, but I promise taking a partial derivative is really not any more difficult than taking a normal derivative. And in fact, all of the tools that you learned about taking normal derivatives will apply equally well to taking partial derivatives. So what is a partial derivative? So a partial derivative tells you how a multivariable function changes as you vary only one of its arguments. So what it tells you, so you have some function that somehow depends on multiple variables, and you want to see what happens when you adjust only one of these. So this is sort of just like taking a normal derivative. So if you have a function f of x and you take the derivative of it, that tells you how it changes as you vary x. So for instance, if f of x was telling you about the position of the particle, then you take the derivative that tells you about the velocity. So it's telling you how the position changes as you change time. So let's be a little explicit about this mathematically. So if we have some function f, which depends on many variables, so as many as you want, as long as it's more than one, so x, y, all the way up to z, whatever you want to call them. And we want to see how this function f changes as we change, let's say, the first variable x. So we want to see how f responds to changing x if everything else is kept constant. So the way these partial derivatives are written is how I did it here, where we use some curly d instead of the normal d that you use for derivatives. So this is to tell you that it's a partial derivative rather than a full derivative. You'll often also see this written as f sub x, which tells you that it is the derivative of f with respect to the one variable x, the partial derivative of f. And what is this? Well, really, it's just the derivative of x, the derivative of f with respect to x treating all else as constant. So I think the easiest way to see how this actually works in practice is to do some examples. So let's consider some examples. So let's say we have the multivariable function f of, let's say we have x, y, and z. And we want to see how this function changes as we vary f with respect to one of these variables. So let's just write down some function. So let's say we have 2xy squared plus, let's say, x squared times the cosine of z. This is just some random function that I just made up that depends on x, y, and z. So first, we want to see how this function changes as we change only x, keeping both y and z constant. So the partial derivative of f with respect to, so let's say, x is given by, so now only x is varying here, right? And I said that we're treating y and z as though they're just constants. And so we have, so 2y squared, that's just a constant, comes along for the ride. And now we're taking the derivative with respect to x, which is just 1, as you know. And so the first term is just 2y squared. Now we're treating, in the second term, we see z is just a constant. So again, cosine z is just a constant. That comes along for the ride. And now we want to take the derivative of x squared, which is 2x. So we can write this. This is 2y squared plus 2x cosine of z. And that's the partial derivative. See, I told you it's just as easy as taking a normal derivative. All of the rules that you learned, the power law rules, things like that, follow in exactly the same way. So maybe next you want to see how f varies as you change y. So the partial derivative of f with respect to now, let's change it with respect to y. So now x is treating as a constant, and only y here is the only thing that we're treating as a variable. So we're taking the derivative with respect to y. X and z are both going to be constants. So again, we see now the 2x. These we're just treating as a constant. They come along for the ride. And then we take the derivative of y squared, which is 2y. And then the second term here doesn't depend on y at all. And so that's just a constant, and the derivative of a constant is 0. So we just get plus 0. And so simplifying, this is 4xy. And then finally, to complete our study of partial derivatives of this function, we could take the derivative of f with respect to z. And so, or I guess we could use a different color for z, blue, if you can see that. So now we see z is only in this last term, cosine of z. So again, the first term now, if we're taking the partial derivative with respect to z, x and y are constants. So the derivative of a constant is just 0. Plus now the x squared is a constant. That comes along for the ride. And we take the derivative of cosine of z, which is negative sine of z. So again, we can simplify this to x squared sine of z. So you see, as I promised, hopefully, taking the derivative of this function, the partial derivative of this function, is just like taking the normal derivative of this function. All you do is, if you want to take it with respect to x, then you treat everything else as a constant and then take the derivative as you normally would. Now I should add that you can, of course, also take higher order derivatives. These were all first order derivatives, but it would be a good exercise for you to try to take second or third order derivatives. And so what you could do, for instance, is take the second derivative of f with respect to x, which then you just take the derivative of this here with respect to x. So you'll see the first term will go away. That's just a constant. The second term is just linear in x. So I challenge you to do that as an exercise. And it'll be important to note that you could also then decide to take a mixed second derivative, where you first take the partial derivative of f with respect to x, and then maybe you take the partial derivative of f with respect to y. And so then you differentiate this term, now treating x as a constant, and differentiating with respect to y. So I think that's all I have to say. Hope you enjoyed the video. Let me know if you have any questions, and I'll be happy to answer.